All right, cool. But here's our lesson plan for today. I'm going to start with the quizzes this time, and then we'll talk about distributed loads, method for solving beam graphs. So that's your shear force diagram, axial force diagram, and bending moment diagram. Yeah, I'll touch upon axial force diagram briefly, but the main focus will be on shear force and bending moment diagrams. I think it should prove pretty useful in your labs because I think your lab assignment is all about making a shear force diagram and bending moment diagram. But yeah, and then we'll go over the questions which are in the middle, the ones provided by the school. We'll have a break, and then I've pulled some harder beam questions, which you can see online in my Google Drive in the extra practice section. Yeah, because I don't think the questions in the workshop are like hard enough. I don't know how to say that without like sounding like, yeah, like when you're learning it, it's hard, but you'll find that they can get pretty hard. I don't know. And then like I actually want to talk about machines and frames. It's something which in my last few workshops I've, kind of hinted at. And I think with the mining school, they might like exclude it from the lecture content or something because they don't really explicitly talk about it. But I feel like learning machines and frames really helps with your understanding of statics in general. So if you want to build upon your statics theory in preparation for the midterm, I think it's a good idea. But yeah, and then, yeah, so we'll just get started. I'm going to check Teams to see if there's any questions. Transcript again. Yep, looks like everything's okay. So yeah, as promised, we'll start with the quizzes. Oh, oops, that's the wrong button. So there's a QR code. So if you get out your phone, scan it. Yep, you know the deal. Yeah, correct me if I'm wrong, but this is the last workshop this week, right? And then, yeah, Friday's your midterm. Should be online, 6 to 7. And you can schedule in a lab as well sometime this week, I believe. And there's sometimes less for maybe early next week as well, I think. Yep, just give a couple more seconds to join. We all good? Yep. Oops. Checking the chat. We all good? Awesome. Get started. You can hear this music a lot. Alright, we'll give like 20 more seconds. Is that alright? Oh, I think this we've done. Yeah, we'll give 20 more seconds. 15 now, I guess. Alright, 5 more seconds. Yeah, I got a message in the chat. Is the quiz not working for anyone else? I hope you mean this quiz and not the something to do with like an assessment. But yeah, if it didn't work for you for this quiz, it's not a problem. We'll just discuss like the answers. So we'll end the quiz right now. Congratulations to these people. Very well done. Yep. Cool. Alright, let's look at the questions. So, you know what I'm interested to see? This first one. Alright. Oh wow. We're good. We're looking good. We're looking good. Looking solid. Do these have captions on them? Anyway. Yeah, looks like we're still doing well. Let's see how it is later in the term. Okay, so question 2 is, which type is not a distributed load? So yeah, it's a point. So point distributed load is actually like contradictory because it can either be a distributed load or a point load, right? So yeah, that one's fake. Triangularly distributed load and trapezoidally distributed load. So in the lecture slides for this course, I didn't see it like phrased like this. I saw it phrased as linearly increasing distributed load, and yeah, just like it's kind of worded like that. But I don't know, in the civil school and in my head, it sounds more logical to describe the shape of the distributed load. So I prefer triangular, trapezoidal distributed loads. Yeah. But those are real ones. And then UDL, I've mentioned it, I think, in the previous workshops, but that stands for uniformly distributed load. But yeah, I don't know. I've seen, I think, maybe not in this course, but in future courses, they might just refer to it as a UDL. So yeah, it's a pretty common term. Bless you. Yeah, and then, so this question is, which of these two types of diagrams are interlinked? And then you take multiple of them. So yeah, the shear force diagram and the bending moment diagram are actually linked. And I can explain a bit further when we're doing the questions on why. And then, yeah, the axial force diagram isn't directly linked to these, but I can, yeah, I don't know. I kind of didn't word this question in like the most clear way, but we can see how they interact as I give an example. Actually, you know what? I'll give an example right now. So we'll do it up here for now. Yeah, I know like not everyone has had time maybe to like watch the lectures live. So I know some people like to go back and watch lectures before attending like the workshops, and that's fine. So I'll just like briefly touch on what we're talking about when we are talking about graphs first. So yeah, so you have a beam, right? Simply supported beam, and let's say it has distributed load, uniformly distributed load on it, like this. Something like that, right? Basically, as an example, Okay, we're going to call this point on the left point A, and this point on the right point B. And if we utilize Newton's third law regarding free body diagrams, and take the cut, and if we cut like the beam AB and expose the internal forces acting on the beam, we get something that looks like this, right? I'm just going to draw it in a perspective kind of drawing. So that's our beam's cross section, right? Oh, sorry. Actually, I'm going to draw it in 2D, right? So what happens when we expose the inside of a beam, right? I actually forgot my sponge today. Wish I had my sponge. It would help with this kind of description. But we expose the shear force. So that one's a shear force. Expose the axial force, the internal axial force, which again is like tension and compression and stuff in the beam. And we expose the bending moment, right? Internal bending moment. Yeah, so what we're looking at essentially is this side of the beam. This is left-hand side notation. And in a question later, we'll see how right-hand side notation looks, I guess, with an exposed beam. But yeah, all I've done is that's like the zoomed in version of the beam, right? And yeah, so let's go back to the question real quick. It was about, yeah, so basically what a shear force diagram, an axial force diagram, and bending moment diagram is it's a description of the internal response of the beam along any given point in the beam, right? So in this particular case, this is a pretty common case. So we have a simply supported beam. It has a uniformly distributed load on it. And when we solve for the reactions, right? 4 times 3, 12 divided by 2. We have 6 and 6 on the support reactions, right? And if we want to draw, what I'm going to do is I'm going to move this. If we want to draw the shear force diagram of this beam, right, it'll look something like this. Maybe I'm jumping ahead a bit, but yeah, okay, sorry. It looks something like this, right? And that's due to, so we have the support reactions, which we can solve using equations of equilibrium, right? And at this point in the beam, the normal force of the reaction A, the support reaction A, is causing the beam to experience a shear of 6 kilonewtons, right? And as we continue along the beam, we have this distributed load, a uniformly distributed load, that's going to cause this kind of like let me think about how to explain this. So maybe it'll help if I draw the bending moment diagram. So the bending moment diagram would look something like this for the beam, right? So basically in the middle of the beam, that's where the max bending occurs, but there's zero shear force there. And the bending moment diagram is linked to the shear force diagram because the bending moment diagram is the integral, right? It's the integral. With respect to x, right? So whatever area that this triangle is, is basically is equal to that point there on the bending moment diagram. So the max bending occurs in this beam in the middle for a simply supported beam with a uniformly distributed load. And the max shear happens at the supports, right? Yep, so that's how they're interlinked. For axial force, unless you have like a diagonal point load, for example, you might not even see axial force happening on a beam, right? Because axial force is all about compression and tension, and whether the beam is in compression or tension. So axial force is more like what you see happening in a truss. And for the civil school, it happens in frames as well, but we never need to derive the bending moment diagram or shear force diagram in this course for a frame. So you'll only ever see a horizontal beam, and you'll only have to do it for that. Yeah. Sorry, I know that was a lot very quickly. Does anyone have any questions about that? No. Yeah. I'm going to check online. We're doing okay. Okay. So that's the general gist of it. Let's go back to the quizzes. I'll finish up explaining the questions, and then I'll have a bit more structure to my rambling, hopefully. So let's go to this one. Oh yeah, so a non-linear varying distributed load, right? Okay, let's go to Discord here. So for reference, that looks something like this, right? So say we have a cantilever beam, right? Fixed end, free end on this beam. If we have distributed load that looks like that, for example, that's an example of a, that's an example of a non-linear varying distributed load. In other words, it's not one of the other ones that we described. It's not uniformly distributed, it's not triangularly distributed, it's not trapezoidally distributed. And so it's kind of a catch-all for like those other ones, right? And so the question goes, the formula to find the magnitude. And the correct answer is the integral of the distributed load with respect to x. Yeah, so this was briefly described in the lecture, but you'll see the formula in my notes in a bit. The other ones are just like kind of tricky. Yep. All right, the formula to find the centroid of a nonlinear varying distributed load. So yeah, for our nonlinear varying distributed load here, this whole distributed load can basically be summarized with the magnitude, right? Which is what we were talking about before and what the formula in the lectures was describing. But what we're saying for the centroid is pretty much this, which is the center of area, pretty much the area of this shape. And we can describe it from, for example, if we call this point O, yeah, some of the questions might say like, from point O, how far is it from the centroid of the varying distributed load, right? Yeah, that's what we're talking about. And so, yeah, it's basically that formula there. Yeah, and then the entire point of finding the shear force, axial force, and bending moment diagram is because it's useful for designing beams and structures and for your lab reports. So, yeah. I think this is a good topic to practice. And yeah, I find it useful in future courses as well. Okay, looking good online. All right, cool. Do we have any questions in person, or are we okay? Okay, cool. So, yeah, so we'll start with talking about distributed loads with a bit more structure, and then methods for solving beam graphs, right? So for the uniformly distributed loads, there's two ways to write it. Sometimes you'll find me writing this way, which is the lazy notation. Those little like arches are pretty much just downwards arrows, but it's just saying this pretty much. And so if we're talking about everything in terms of what I was describing before with a magnitude and a centroid, yeah, the properties of a uniformly distributed load are pretty easy to calculate. So the resultant load, right, of this entire distributed load is equal to whatever load it was, right? So let's call it W. Let's say, for example, it's 4 kilonewtons per meter, right? And let's say this is 4 meters, right? So the resultant load would be 4 times 4, because it's 4 per meter, and we have 4 meters of it. And so all up, the resultant load is 16, right? In this case. And so when we talk about a distributed load, you also want to find the centroid, right? And so it's half the length of the distributed load, right? So in this case, it would be 2 meters to get to where the resultant load is. And so just be careful. So if you have the distributed load not actually take up the entirety of the beam, for example, if this was 3 meters, for example, right, then everything changes. So R would be over here now, right, because it's for however long the distributed load is. And to get to the centroid of it, would be 1.5, right? Yep, that's kind of how it works. Same for this notation, exact same thing. Okay, so now when we're talking about triangular distributed load, it's basically, there's two types. There's the linearly increasing load, which I think was the wording in the lectures, and the linearly decreasing load. So they look like this accordingly. They're both triangles, right? But it's just whether the big side is on the left or the big side is on the right, right? And so when we're talking about the resultant load, it happens at 2/3 of the length. That's 2/3 from the small side, or alternatively 1/3 from the big side. So these are pretty common ones, and yeah, you'll probably come across it a lot. But yeah, so not bad. Sorry for the people copying it down. I'm just going to scroll down. My notes are also in the Google Drive for what I'm copying. So if you miss anything that I write, feel free to look in the drive, and you can scroll at your own pace. So, right, for a trapezoidally distributed load, there's the linearly increasing load and the linearly decreasing load. Okay, and quickly, I'm just going to jump back. For linearly increasing and decreasing triangular loads, usually what happens is this is called W max, right? Because the small side for a triangle is 0 kilonewtons per meter, right? The smallest magnitude. But W technically changes, right? So we just call that W max because that's the highest it'll go, right? And yeah, and so for a trapezoidally distributed load, sorry, I'll zoom out a bit so it's a bit easier to read. It's a bit easier to copy down what I just said before. This one will be W max. These two will be W max. But this we can call W min, because it also varies, right? And it varies linearly. And so Yeah, it's only gonna vary between W min and W max. And in terms of a resultant magnitude and resultant centroid, I don't think there's like a clean formula for it. So the best thing to do is use the integration formulas, which I'll show you down below. It's basically these ones here. And for my notes, copy them down here. All right, so for the magnitude of a distributed load, So to describe what's going on here, firstly, instead of describing it with W max, W min, we described it with a function. If you recall, like U-turn graphing, this could be a parabola, this could be, if it was a straight line, it'd probably be a trapezoidally distributed load. So it'd probably be like a parabola, or I've seen one with a square root x. It's some function with respect to x, right? And yeah, and so WO just means the initial distributed load magnitude, right? Yeah, so that's usually what it refers to. And so in terms of a formula, we can do this. Where you can plug in the function that they gave you, right? And yeah, sorry, that's what my quizzes was describing in the question. But yeah, the wording's pretty confusing, to be honest. It's easier to look at the formula than describe the formula in English, right? And for the centroid, it looks like this formula. Right, and that R is this R, right? So it's that numerator divided by the magnitude of the distributed load. And so in other words, you can actually just put that part down here. Same thing, right? And so when you're solving for your trapezoidally distributed loads, I would stick to these formulas. And if you're solving for anything more complicated, definitely use the formulas. Yeah. Yeah, I see a few people copying this down, so I'll just give it a second. I'll just check the chat as well on my phone. Yeah, looking okay. So I'm gonna move on. Oh, does anyone have questions? Okay, cool. All right. So pretty much, all right. So, yeah.
What's W previous?
Yep.
What's W?
Oh yeah. So W just stands for any distributed load. So usually we use P to denote a point load when we're talking about it, like algebraically, I guess. And W is just to describe any distributed loads. So for all of these examples where I'm talking about distributed loads, I'd be using W. Yeah. But if you're talking about this part here, W is a function with respect to x. So it's almost like you're graphing, right? You know, y equals mx plus b for a straight line. That's kind of how it plugs in. So W will be the equivalent of y, so the up-down function, right? On this, yeah, free body diagram, yeah. Oh, sorry, I'm going to come over. Could you repeat that, please?
I mean, the W is the sum of the edge
Oh, no, sorry. So, I'll go over to the laptop so I can hear it as well. So, just to be a bit more clear, sorry. Pretty much W describes the up-downness of this graph, right? So it's analogous to Y on, like, using this notation. And I believe what you're referring to is R. So R is basically the resultant distributed load. So R would look something like this. If you were to turn it into a point load, right? Yeah. So R would be the sum of the distributed load. Yeah. Yeah. Good questions. Thank you. Do we have any other questions? Okay. Check online as well. Looking good. All right. So for solving beam graphs, right? There's pretty much two ways to do it, but I would say in general, for these type of questions, you can solve for support reactions as your first step. Yeah, if you remember in last workshop when we were talking about trusses, you don't necessarily need to solve for all of the support reactions, right, straight away. Sometimes it's a waste of time because you might not need it, right? But I would say 100% of the time you need the support reactions. I think. Oh, I can think of an example where you don't need the support reactions actually. So let me just draw one. This is cantilever, and say we have this complicated load on it. If you take the cut, right, from point A to B, yeah, so that's point A and that's point B, right? If you take a cut, you can choose to go left to right or right to left, pretty much, right, when you're solving this. And so if you go right to left, and consider that your X direction, you don't need to solve support reactions, right? Because it's a freehand, there's no support reactions that you need. But that's like a pretty rare case. I would say like 99% of the time, you need to solve for support reactions first, yeah? So that's your exception. I'll leave that there. But yeah, so now we have to look at a beam and see if we can do the shortcut, pretty much. So if what I was saying before didn't make much sense with what I was doing on the first page, it's because I don't think in the lectures or in this course they teach you the graphical method, which is why I call it, right? So the graphical method is great because it's pretty much faster, easier to do than the other method, but there's limitations because it can't solve certain problems. I'll give you an example of something it can solve and something it can't solve, okay? So, in what I was describing before in the quizzes, we have that simply supported beam. Let's say, just for lols, we'll swap the, normally I draw like the pinned on the left, roller on the right, but yeah, so that's a roller, whatever. And then we have our UDL, like that, right? So with the graphical method, I actually don't even need to take the cut here. What I can do is I can solve for the support reactions. So let's do that again. Let's say this one's 3 kilonewtons per meter on this distributed load, right? Uniformly distributed load, right? And then here, let's say this is 5 meters. Because this is symmetrical, right? And even the external loading is symmetrical, I can find the magnitude of the support reactions really easily, because what I do is I find so the distributed load is 3 per kilonewton, right? 3 kilonewtons per meter, and it's multiplied by 5, which is the length of the beam. So that's all of the downwards force pretty much. And so each of the supports is taking half of all of the downwards force, right? And it's taking it evenly because of, the shape of the beam. So each support is taking that much, right? And so now, on a shear force diagram, with the graphical method, essentially how it works is we go up by the support reaction on the left, if it's a simply supported beam, because whenever we're analyzing left to right, and and then you reach your support reaction, you go up by that magnitude, right? Or if it's a negative value, you go down by that much, right? So that goes up to 7.5. And then it linearly decreases if you see a uniformly distributed load. And then it goes up again by 7.5, right? And we know that since it's symmetrical, this is 0 in the middle, right? So the graphical method is very quick. And I really like it because, I don't know, it doesn't take very long to do questions. But yeah, it can't solve certain problems. So that's an example of something it can solve, right? Granted, I haven't drawn the bending moment diagram on that one yet, but yeah, you can draw the bending moment diagram quite easily based on the shapes here. We'll get into that a bit more when we do our practice problem. But here's an example of something it can't do, okay? So we have our simply supported beam. And then say we have a triangularly distributed load like this, right? Right, and the max distributed load value magnitude is 15, right? And yeah, so here we'd actually have to solve for our supports, right? Whatever that would be. Yeah. I'm not going to do the calcs for this because it's just an explanation, but you solve the supports first, right? And then for your shear force diagram, it's going to look something like this. So since the load is decreasing, right? So first of all, it goes up by this much, which is the first support reaction. Let's call it RA, not RB maybe. So this goes up to RA, right? And then, so because it starts low and then goes high, what happens is the slope on this shear force diagram starts at 0 because at the very start, there's no loading, right? So it goes like that. And what's going to happen is it's going to start decreasing more and more, like that, right? And then it's going to have a shape that looks like that, okay? And then we go up by RB. So that's going to complete our shape for the shear force diagram. However, the problem with the graphical method and why it falls apart in these kind of questions is you're going to find it very hard to find where it reaches 0 here, right? Where the magnitude, where the shear force diagram crosses over to 0, and therefore when we make our bending moment diagram here, yeah, it's going to increase to that point, which it has 0 slope, but then yeah, you're going to have troubles finding that value of m. So we have to employ our other method, right? So I'm just going to move everything. We have to employ our other method, which is what we learned in lectures, which is what I'll call the algebraic method. Okay, so this one's a bit harder. It's slower, takes a bit longer, but it can solve any problem in this topic. Right. So if you look at the workshop solutions after they're released, done by the mining school, you'll see that they solve the following problems, which I'm going to show you using this method, right? They're going to use the algebraic method, and that's probably what they've taught in the lectures as well. But whenever you can use this shortcut, and the wording of the question just asks you for the shear force diagram, bending moment diagram, you should, because it's like 10 times faster, right? So anyway, so that's like a lot of theory and a lot of talk, and you might have a lot of questions. So actually, if anyone has questions right now, feel free to ask away. Yeah.
How do you know what the diagrams look like? Just
A lot of practice.
practice.
Yeah, but I think like once you do your practice, you'll get the hang of it as well. But yeah, that's the idea with the graphical method is it's graphical, right? If you're like a visual learner like me, you might prefer it because things seem to fall into place once you do enough practice for it. Yeah, yeah. Yeah, I'm gonna check the chat as well. Will we ever get another opportunity to ask questions for extra practice questions other than this workshop? I mean, you can always leave a comment on Teams about the extra practice questions, or you can email my email. It should be in the first lecture slides. Yep, and I can try to get back to you whenever I can about certain problems you might have encountered about those practice questions. Yes, pretty much. Thank you, Sigar. Yeah. Okay. So, I think it's best to do some questions. So here's how I've structured today's lesson, right? Yeah, I want to do these questions quickly, and then we'll take a break. Then you can get like your order and that, because these questions might take a bit longer. That's why. So yeah, I guess in the interest of time, we'll do the questions now. Okay, here we go. So here's the first question, and all it's asking for is a support reaction. So it's not too bad. We don't need to draw a bending moment diagram. We don't need to draw a shear force diagram yet. What we need to do is figure out how to calculate this distributed load, right? So I'm pulling up my notes real quick. So I'm going to do the calcs. Okay. So yeah, pretty much we have our uniformly distributed load, but it doesn't act over the entire simply supported beam, right? And so we want to find, actually there's two ways you can do it. One way you can do it is you can pre-calculate the resultant load and then pretend that the uniformly distributed load isn't there. But how I like to do it is I like to just do it in one step. So it'll look like this. So first, I take the sum of the moments, right? Because if we take the sum of the forces in the y direction, we'll have two unknowns, so that's not good. We can take the sum of the moments about either A or B. I'm going to choose to take it about A. And so if we're taking it about A, then By is going to be positive because this arrow is going to cause a counterclockwise spin, right? And the distance is 0.8 meters away, right? So that's our lever arm, right? So this shouldn't be too unfamiliar. Next, so with our distributed load, do the magnitude of the distributed load multiplied by its length that it acts over. So now this is actually the magnitude, right? And then, let's move this. And then we multiplied by the lever arm, which, remember, if this was a point load, basically it's halfway across here, right? Yeah. And so we do 0.3 plus 0.25 to get from here to here, right? So what I do is I'll just write that as 0.55, right? So that's your lever arm. Cool. And then by, so now we can solve this because we just have our one unknown. So by is 1.375 kilonewtons, right? So now that we have by, it's that there, we can solve for ax or ay next. We know that sum of the forces in the x direction is equal to ax, and so ax is equal to 0 kilonewtons, right? That's all good then. And then lastly, we do sum of our forces, which is ay plus by, and we have to minus magnitude of the distributed load, right? Which was 4 multiplied by the length of the distributed load, right? To get that resultant for the magnitude here. And yeah, just be careful not to multiply it by the lever arm if we're doing sum of the forces, right? Yeah, all good. It gives us that ay is 0.625 kilonewtons. Okay, so that's the first question. Do we have any questions about that? Are we okay? All right, because I'm probably going to skip the support reactions in the interest of time for the next few questions, all right? So just make sure you got this one down first. I'm going to check the chat on my phone. Where are the questions from? Yeah, all good. All right. So next, the question asks to find the moment at B, and so I did a pretty bad job drawing this. So it looks like this, right? And we have a point moment. Yeah. Have we run into a point moment before? No? Yes. Okay. Basically, we have our point loads, right? So, you know, stuff like that, for example. That's not actually on the question. But point loads and like distributed loads are forces, right? But a point moment is basically a moment at a point, you know? And so they can either be clockwise or counterclockwise. When we're solving for the support reactions, it's only ever going to affect the sum of the moments part, and it's not going to affect the sum of the forces part. Okay. Yeah. And the other question I wanted to ask you guys, just to, you know, it's like a theory question, is this a simply supported beam? Have a think. Okay, so it looks like a simply supported beam because of the reactions, but we actually call it a overhanging beam because of this bit here. An overhanging beam can also look like this as well, right? So that's actually an overhanging beam, but you solve it essentially the same way, right? But yeah, cool. So I'll show you where it plays into effect. So because it's a counterclockwise moment, we add on 1.6 to the sum of the moments. So, but if we took the sum of the moments about point B instead of point A, will we still add on 1.6 or would we subtract 1.6, I think? You still add it on. So this is a point moment that affects every point when we're taking the support reactions. And the reason is because when we take support reactions, we're analyzing the free body diagram of whatever we're looking at, and for support reactions on a beam, that would be the entire structure, right? So as long as we're looking at a point moment, you just simply add it on, or subtract it in the case of counterclockwise, right? Oh, sorry, in the case of if it's clockwise. Okay. So even if it was over here or something, even if this was like 3 or something over here, you would subtract 3 off of these moments here. But it never interacts with the sum of the forces, right? Yeah, so you might, like a question I got in term 2 while teaching was like, does that mean you can put the sum of, does that mean you can put a point moment anywhere, right? And it doesn't affect anything? And the reason is no, because you'll see that, not in this question, because this question, it doesn't ask for the shear force of bending moment diagram, but it affects the bending moment diagram at that point, right? So the bending moment diagram, right, if we were to draw it for this beam, right? I can't really do it in the graphical method without drawing the shear force and stuff first, but just completely making this up. This isn't what the bending moment diagram would look like, but it would look something like this, right? Where it is discontinuous at this point, pretty much. I don't know if that direction was right or wrong, but it has a sudden jump at that point moment, right? So something to keep in mind. But usually the bending moment diagram is continuous, unless you run into a point moment or a fixed support, like a cantilever, for example, right? Yeah. Can you tell there's a lot of content in this workshop? Sorry, guys. So yeah, I'm just checking the chat. I think we're looking okay. All right. So yeah, just so solve for the support reactions now. The rest of the questions, like find the moment at point B, right? So how the solutions do it online is they take a cut on, I think they call this point C. So that's point C, that's point B, right? And then they can take a cut here and analyze it right to left. And then they use the algebraic method, right? But I love the graphical method because it just makes life so much easier, trust me. So you see what it finally is like step by step. And so, yeah, first I like to start by drawing the shear force diagram like this. So you draw like a little graph, XY plane kind of situation. And I usually like to line it up with my free body diagram drawing, just to have it so that I don't have to write out the lengths again, I guess. Actually, you know what? In this case, for demonstration purposes, I will duplicate the lengths over. But it's corresponding one-to-one, right, with our free body diagram, right? So we know that AY is 0.6 and BY is 1.4, right? So when we're doing the shear force diagram and there's a support on the left, the first thing we do is go up by AY, right? So the support makes it jump up like that. We do it in a... Right, support makes it jump up like that by 0.6. All right, and now, so previously the shear force diagrams we've seen have had a uniformly distributed load acting on it, right? But if there's no uniformly distributed load acting on it, the shear force diagram doesn't move, right? In terms of, it doesn't move up and down, right? So it's actually flat here. Because, yeah, from here to here, there's no uniformly distributed load. And then from here to here, I mean, the only thing that changes is the point moment, right? And the point moment doesn't affect the shear force diagram. It only affects the bending moment diagram, right? You got that? So actually what happens is it doesn't affect the shear force diagram, and so it stays flat here, right? And then By, our other support reaction, is 1.4. Sorry, I think I raised too much here. Yeah, and that causes it to go up again by 1.4, right? So that jumps up 1.4 here, right? But what I like to do is I like to just draw, I mean, you can do it here or you can do it here. I just like to write the total, right? So 0.6 plus 0.14, plus 1.4 is 2, right? And then we have that point load, which acts downwards, right? And that causes that to go back down like that. So it kind of looks like that, right? If I draw arrows, you can draw arrows if you want. Yeah, it's just like following, yeah, like a little line, right? Going left to right. Yeah, so that's pretty much all there is to the shear force diagram. So, I don't know, pretty easy. And you don't need to do the algebraic method to get here. The algebraic method, again, would normally take a lot longer. Checking the chat for questions, looking okay. All right, but here's the next step, okay? So, what I'm gonna do is I'm gonna break this shape up into smaller shapes, right? Because this will be useful for calculating the bending moment diagram, okay? So I'm gonna call this shape 1, and because this is the exact same shape, I'm gonna call this one 1 as well, right? And then I'm gonna call this shape 2, okay? And now we literally just take, find the area of this shape, right? So in the up-down direction, it's the shear force. In the left-right direction, it's the length, right? So it's 0.6 times 0.5 for shape 1, right? If we want to do it in units, okay, it's 0.6 kilonewtons, right, times 0.5 meters, right? And that gives us 0.3 kilonewton meters. See where this is going? Kilonewton meters, right? And then for shape 2, it's very similar, but we do 2 kilonewtons times 0.5, which is 1 kilonewton meter, okay? So this is gonna slot in perfectly when we do our bending moment diagram. And if it doesn't, you know you did the question wrong. Yeah, so for the bending moment diagram, it's gonna look like this. I guess you can call this axis X, by the way, if you want. Call this one M for bending moment. If you want to do it perfectly, you go like, include the units and everything too. That. Okay, so basically the bending moment diagram maps out the area underneath the graph for the shear force diagram. It's just the integral of the shear force, right? Right. And so we're going to start at 0, and because there's no point moment here, we don't have a discontinuity or anything, right? And so it starts at 0, and it will linearly increase because these shapes are on the positive side of the graph, right? So actually, I can actually call this plus and plus, right? And so this point here is going to be equal to the area we calculated, right, above, which is 0.3, right? And then, but we can't forget about our point moment, right? Because when you see a counterclockwise point moment, what happens is it makes it go down, right? It's not up, it makes it go down, all right? So it goes down by that much. So that's basically 1 minus our point moment, which is 1.6, okay? Which is equal to 0.3 minus 1.6, which is negative 1.3, right? I Actually, sorry, that might have just been more complicated. I'm just gonna do that. Okay, so that's where we're at right now for our bending moment diagram. And then basically what's gonna happen is we're gonna add on another one of that shape 1, by the time it reaches here, right? So here, it's negative 1.3, continuing from what we had before, right? Except you add on one of this shape, right? Which is 0.3. And so this is now negative 1, okay? And then what happens is, to close it off, what's it called? To close it off, we have to add on the shape 2, right? So it looks like this. So that's 0, right? Because shape 2 is 1, so you add another 1 onto negative 1, that's 0, right? I kind of drew this wrong. It looks a bit more like this. Yep. Right. And this is with this convention where anything above the graph is going to be positive, anything below the graph is going to be a negative bending moment. But yeah, basically suffice to say, point B, the moment is equal to negative 1 kilonewton meters, right? Because this was point B, right? And that's the value we have at that graph, on a graph at that point. Yeah. Yeah.
What did the point moment force the thing to go down?
Good question. So it's because of this notation. Okay. So for the graphical method, you basically just accept that as fact. But if you did it the algebraic method, you'll see that following our internal forces within our beam's convention, having a point moment will have the opposite sign effect to the shear force, if that makes sense. It makes more sense once we see the algebraic method, I think. But because the graphical method is just like a shortcut, we're jumping ahead like too many steps for me to be able to explain that fully. But it's just due to this sign convention pretty much. Yeah. Right. It's supposed to be, sorry, I'm gonna go back down. Isn't it supposed to be 0.6 kilonewtons times 1 meter? Yeah, it depends how you want to break it up. I see what you mean. You could do this. You could do this shape as just 1 instead, like that. But the reason I decided not to is because the point moment here, the point moment kind of will break up your shape anyway when you're drawing the bending moment diagram. So it's actually smarter to do it the other way. Yeah. Is there any more questions before we move on? Yeah, all good. Oops. Okay, cool. So here I've solved for the support reactions right off the bat, but this is a triangularly distributed load. Oh, wait, this is right. Sorry, my bad. I've skipped ahead. So this is the last question in the workshop. And yeah, so I've solved the support reactions ahead of time, just like with the other questions. And yeah, so we're gonna do the same method because we have if we see point loads and uniformly distributed loads only, it doesn't go to like triangularly distributed load or anything more complicated. We can use the graphical method, right? So I'm gonna draw the shear force diagram. Right? AY, right? AY is 1.125, And so it goes up by 1.125, like this. And now, because we have a uniformly distributed load acting downwards over the run of this beam, what happens is it's going to go down like this before reaching point by, right? And how much does it go down by? It goes down by, basically you go like this in your head, you go 1.5 times 2. Right, 2 because it's 2 meters before anything happens, right? So basically, this number minus 3. That's basically what you do in your calculator, right? So that's negative 1.75. There's some noise happening here. What's going on? Sorry, I'm going to mute you. Okay, so yeah, and then next what happens is by. Sorry, scrolling a lot. By is this amount. So on your calculator, you go negative 1.875 plus by, which is 3.375, and that brings us up to 1.5, right? And then there's no more discontinuities on our shear force diagram, yeah? And so it just goes down to 0. So now we have our shapes, and we're just going to find the magnitudes of the shapes. Let's call that shape 1, shape 2, shape 3, yeah? And so for shape 1, we do, it's half the area, right? Because it's a triangle, half base times height. So half, the height is 1.125, and then, okay, here's the thing. We don't know this distance, but we can find it fairly easily using similar triangles. So that's what I'm going to teach you guys right now. Oh, sorry if you're copying this down on like a physical notebook. I'm going to move this quickly. So I'm going to move it down because here I've assigned some space to find B, right? All right. So basically, this entire distance here, right, is 2 meters. Yeah. And that distance there is 1 meter. Here's how you find B. Because we have 2 triangles here, yeah? Oh. Basically, we know that the slope of these 2 triangles are the same. Right? It's like the same slope going down that way. And so all we do is we literally plug in the rise, which is our vertical rise, over the run, which is the distance x that it covers, right? And so it's 1.125 over b, which is our unknown, right, is equal to the rise, which is, so actually if you plug in the positive number, it's going to give you the right number anyway. So like all these triangles have the same slope, right? So when you're solving for it, yeah, basically just stick with a positive number here, you'll be fine, right? That's what I'm trying to say. Because, yeah, so that's the positive version of that magnitude, which is the rise in the triangle. And then the run here, what you do is you take that length and you subtract b, okay? Because this distance here is 2 minus b, right? The difference in the total length of that subtracted by our unknown. So now we can solve for b. So algebraically, you can go like this. right? What we've done is we've cross multiplied on both sides, and then now we just simply solve for b as if it was a unknown. Yeah, just like normal. And so now we know that b is 0.75, right? Now we can continue to find the magnitudes of our shapes quite easily, right? So that first triangle, I've just put in 0.75 for the base of the triangle now, and that gives us 0.422 kilonewton meters. Okay. And keep in mind, this is a positive number, right? Because the triangle is above. But our next one's going to be a negative number because the triangle falls below the graph, right? So our magnitude is negative 1.875, right? Negative because the magnitude is negative here. And we have to now multiply the base by 2 minus b, right? It's 2 minus 0.75, right? So once we punch that into the calculator, you'll get that that is negative 1.172, right? And lastly, our shape 3 here is half, simply 1.5 and 1. That one's not problematic at all. We're all good. So it's just 0.75 kilonewton meters. Right, that's that triangle there. Yeah. Any questions so far? Is that okay? Cool as. All right. So now I'm going to do the bending moment diagram. What I'm going to do, make that a bit smaller, give myself some space. I'm going to line it up with the shear force diagram vertically so that I don't have to redraw my lengths, right? Am I working out? I'm going to do that. Actually, I'll do that. Okay, so because we don't have any point moments or fixed supports on the left-hand side here, this is what our bending moment, this is what our free body diagram looks like. Our bending moment is going to start at 0, okay? And then it's going to go up to a certain point. So I want you to think about how the slope is going to work, right? Pretty much here, when the shear force is 0, the slope of the bending moment diagram is going to be equal to 0, okay? So what I mean is, because there's a positive triangle, it's going to go up, right? It's going to go up. So it'll be somewhere above here, and then it's going to be flat. Oops. It's going to be flat. The slope will be flat on the bending moment diagram. And therefore, is the shape going to be this or this? Have a think about it. Because the slope is flat, the shape is going to look like that, okay? And then it's continuous. This slope is going to be the same on this side of the triangle and this side of the triangle, right? So we're going to continue the same slope and go down like this, right? And so what are the magnitudes of these triangles? At this point here, it's simply equal to 1, which is 0.422 kilonewton meters, okay? And here, continuing left to right, it's going to be 1 plus 2, and remember 2 is a negative number, so that's 0.422 minus 1.172 on your calculator, which is negative 0.75 kilonewton meters, okay? And now, now we have this big discontinuity in our shear force diagram, right? And so the slope is going to flip suddenly, right? But we also know that here the slope will be 0, right? And so therefore, it's going to be flat here, right? What shape is it going to be? Is it going to look like this or this? Since the slope has to be flat there, it's going to look like this, right? Because the other way, it wouldn't have a flat slope there, right? So here's our bending moment diagram. And yeah, that's the question. Do we have questions? No? Yeah, no? I'm going to check online as well. Oh yeah, I haven't done the attendance yet. Cool. So actually what I'll do is, yeah, I've been talking for a long time right now. You haven't had your break, so please, yeah, you deserve a 5 or 10 minute break. Yeah, so yeah, just chill. If you need to get water, go to the bathroom, and we'll continue after that. That's pretty much all of the workshop questions, right? But yeah, if you stick around, I'll run you through the algebraic method as well. And if you have to go or whatever in person, I would highly recommend watching the recording of what I'm about to do, because this one actually takes longer to explain, right, compared to that, which I don't know, that already took quite a while to explain. So yeah.
Sorry, how do we find point B?
Sorry, it's not point B. What they called it is the length B. I don't have the exact question up. It says something along the lines of like, what's the length B where the shear force diagram touches?
Bending moment is 0.
Oh yeah. Wait, the bending moment is 0 or the shear force diagram is 0? The bending moment is 0. Oh right, I see. Oh, sorry, I misinterpreted the question. That's my bad. Okay. So they called that length B. Is that right? Okay. So let's call that D. Sorry. And we can calculate B. Okay, so they mean this, right? And so in order to find that, essentially it's it's basically one of these triangles up and then the same triangle down, right? So that it arcs and then reaches back to the same point. And so I'll draw that again. So it basically looked like this, right? Right. And then at that point, your bending moment is 0, right? And we know that this length is D, right? Which is 0.75. And so B is just going to be 2D, right? It's 1.5. Yeah. It's quite beautiful, right? Everything just works out. Yeah, it's great. Yeah. Attendance. Okay, sorry, I'm doing the attendance right now. Yeah. Oops. Yeah, just fill that out, please. Thank you. Have we all gotten that link in person? Yeah. All right. I'm gonna check the chat on my laptop. Okay. No worries. Just have 2 more minutes or so. Just take a break. Yeah, I realized in my notes I didn't include the internal force thing within a beam, so I'll probably just add that on before I upload my notes to the Google Drive. It's like the final copy tonight. We'll get started at 7:30, so in about a minute, I reckon. So I'm gonna try this one. All right, we ready to get started again? We've got a lot to get through. That's why, and I want to finish. Hopefully, yeah, without going over time. And especially for the people who came in person, because we had to get home. It's a really late shoot. I was really hoping the time they gave on the draft timetable was 3 to 5. Oh man, that would have been perfect. Now I can get home earlier and cook dinner. But yeah, it is what it is. So here we are. Yeah, cool. Let's get started again. All right. Triangularly distributed load. So as soon as you see this, you can't do the graphical method, at least for this part of the beam. In this question, the entire beam is the triangular distributed load, right? So I'll just jump straight ahead to pretty much what they taught you in the lectures, which is the algebraic method. And yeah, I've included quite a few extra practice questions for today's workshop, because I feel like the difficulty in what they've provided in the earlier ones, you don't really get all the catch-all cases. You don't really get all the niche cases, right? You get the general cases, but it's good to practice because then you get the niche cases as well. Yeah. And so because I don't know what's in your midterm, I'm trying to give you guys as many resources as possible so that, hopefully it's not on me, if you're missing anything, because then there's plenty to practice with, right? Yep, so I've done what I did before, and I've solved for the support reactions first. Something interesting to keep in mind is that because this is a triangle, right, our magnitude is now going to be half base times height, right? Not just base times height, like in with a uniformly distributed load, which you can kind of treat like a rectangle, if you want to think of it like that. And so that's where that half comes from, right? Half comes from the the half comes from the fact that it's triangle. And with the lever arm, what are we talking about? We took it about B, and so 1/3 of the length, right, from the big side is 1 meter, so that's where that comes from. But if you took the sum of the moments about A instead, you'll have to use 2 meters for the lever arm, right? Yeah, so to the 1/3 off the fat side of the triangle, pretty much, right? So you remember it? Okay, so now we've solved for our supports. Here's where it gets a bit funky. So pretty much, this is point A, this is point B. We're going to take a cut of this beam, and we can either choose to go left to right or right to left. So far I've only talked about left to right notation. Sometimes it's going to be advantageous to go right to left instead, which you'll see in the next question. But for this one, we'll just do the normal case, which is left to right. Okay. So we're going that way, right? So for cut, I'll put it down here. We're looking at cut AB. What I like to do with this naming convention is I label it from the point. It's like 2 points, right? So in this case, it's labeled A and B, and I write it in the order which I'm going, right? So if I was going right to left, I would call it BA, cut BA instead, right? Yeah. So anyway, and the other thing to do is you should write down your domain for X, okay? So in this case, this beam is 3 meters long, right? And so our domain goes between 0 and 3. Okay, actually, I think it's more accurate to do that, to be honest. I'll explain why later. But yeah, so that's the domain, right? Okay, so what I'm going to do is I'm going to redraw this beam with the cut, okay? And here's the distributed load, okay? And we're on the left-hand side of the beam. That's point A there, and AY was 0.75, right? So this is going to be 0.75 here, okay? And so with what I was talking about earlier on that first page, the one with the internal forces of the beam, here's where we're going to have to utilize it. So if we're going left to right, the shear force that we're going to be calculating is going to be this kind of like unknown that we're going to point downwards at the cut here. Okay. And M is going to be our internal bending moment, right? And it's also acting at that point here. So these are just kind of, they're not like the most accurate drawing, but people know what you're talking about when you draw it like this, right? Because technically the line of action of that V should be here, right? And that M should actually be like that because it's acting about that point. But people know what you're talking about when you do that, right? Okay. Here's something to notice, right? So what is the slope of this triangle? Okay. The slope is equal to rise over run, which we know because it's linear, right? It's linearly increasing in this case. And so, if we look on our free body diagram, the rise, let me just highlight it. The rise is 1.5, right? And the run is 3 meters. So it's the same slope as what's represented on our free body diagram, right? Like that, right? So the slope is 0.5 meters. Is that right? 0.5. I wouldn't include units. Just to say slope is 0.5, right? Might get confusing. Because what we're gonna do is we have to work out the height of this triangle, except this is gonna be a function of x. Because if you think about what we're actually doing with this technique, is we have this cut that's gonna actually be moving. So it's gonna start here, and we're analyzing, we want to derive some sort of function for this cut as you go along the entire beam like that, right? So it's actually this varying distance, which we're going to call x, right? And so the slope is going to stay the same for this triangle, but this height is going to be a varying height, right, as we move our cut along that part of the beam. So this height here is actually going to be slope times run, which is going to be our rise, right? And the rise is going to be 0.5 times x, because I should draw this a bit better. Because x represents the distance that we've traveled along our beam, right? So that's actually our run, technically. So anyway, yeah, so the slope times the run is going to be the height of, the varying height of this triangle, yeah? And then, yeah. Okay. Gets even better. So what we're going to do is we're going to derive a function for v and m, because v and m is what we're actually interested in. We're interested in the internal forces, including the shear force and the internal moment of this beam. And we want to derive an expression for that. So I'm going to do v first because v is easier to explain. So sum of the forces in the y direction is equal to 0, yeah? We're familiar with this, except we're not taking the sum of the forces in the vertical direction for the entire beam anymore. We're only taking it about this free body diagram cut, right? And so all we've exposed with this diagram is 0.75, which is our force at point A, right? Our vertical force at point A, minus V, right? V is our unknown that we're solving for, but we can't forget about our triangle as well, right? Which has a varying distance and a varying magnitude, yeah? Which sounds scary, but you're still using, like geometry to solve this, right? All we want is to get the magnitude of that triangle, we just have to subtract half the base times the height, right? Because it's a triangle at the end of the day, right? And so the base is x of that triangle, right? And the height of the triangle is what we calculated earlier, the slope times the run, okay? That there, right? So yeah, so now we've accounted for all the vertical forces. So when we solve for v, because we actually want to solve for v, right? That's what we're doing. We get that v is equal to 0.75 minus 1/4 x squared. So what we've actually managed to do is we've managed to derive an expression, or like a function, which describes the shear force at any point along the beam, right? And that's actually what we've been graphing with our graphical method, but we just haven't had to do all these steps to get there in the graphical method. But yeah, anyway. So, but we haven't done the moments yet, right? So the moments is the next step. We're going to take the moments about the cut, and we always take the moments about the cut here in order to just derive our expression. So we do a very similar thing, where let's account for this point. Well, it's a point load, but it's a support reaction, right? But we can kind of treat it like a point load acting upwards, right? So that's 0.75, which is the magnitude of that, that force, multiplied by the lever arm, and the lever arm is x, right? Oh, wait, I've done something wrong here. Okay, I've done something wrong because if we're thinking about the cut, this is going to generate a clockwise moment about it, isn't it? And so therefore, this should be negative 0.75x, right? Because it's clockwise. And then m, right? M with our left to right notation is counterclockwise, and so when we take the sum of the moments, you're gonna add on m here, whereas above you subtract v, right? And so about the question from earlier, pretty much the reason why the point moments make it go down and the support reactions make it go up is because of this notation here, right? Oh, I should do that in a different color. It's because of left to right notation. You'll see the difference is that v and m will always be flipped from each other, and from right to left, you'll get plus v instead and minus m. So m and v will always have like opposite signage to each other, right, when you're solving. Okay, we're not done yet. So the triangularly distributed load here, right? About this cut, it's going counterclockwise. That force is gonna cause it to spin counterclockwise, so it's gonna be positive here. And we have to do half the base times the height, right, which is the magnitude, times the lever arm as well. Right? So it's very similar to what we did before, but we also need to account for the lever arm. And what I'm literally going to do is I'm going to duplicate the magnitude from before. So that's the magnitude. And then multiplied by the lever arm. And the lever arm is 1/3 from the length to the fat side of the triangle, right? So that is x on 3, right? Let me just draw that on the diagram so it's a bit clearer. It's this varying distance x divided by 3, right? That's the lever arm about the cut, right? But now we can just solve for m because we want a function of x, so we can move all the x's to the right hand side and m to the left hand side. Right? So now we have an expression for m as well, right? So this is the algebraic method, yeah? And we can graph it. So for our shear force diagram, right, here's how everything, pans out. You know what, I'll just, what's the whole thing? 3 meters, right? Okay, so how it works is basically we're going to take these functions and we're going to plot it on this graph as if it was an XY plane. And so we start off at 0.75. And guess what that was? That was the AY, So same thing as before, right? Same thing as the graphical method, but like 10 times harder to get here, right? And then you want to subtract by that much. Yeah, so basically you're plotting an upside down, you're plotting a parabola, right? And it's a frowning face parabola, pretty much, because it's a negative x squared, right? So it'll look like this, pretty much. Right. And you'll know that by, right, causes to go 1.5 up. Oops. So that has to be... Do you see how the graphical method, like learning the graphical method first will make the algebraic method easier? Because you'll know these little tricks to plot it perfectly, right? So I would recommend you learn the graphical method, and then once you learn that, learn the algebraic method. Because otherwise, when you get taught just the algebraic method, you're like, what the hell is even going on, right? Because this is like so many steps that you're missing. So this is the way I teach it, and I think it makes more sense. Anyway, so that's negative 1.5 here. And the question's asking for the max moment, yeah? And so before we plot the bending moment diagram, just have a think about this. So, okay. So I'm gonna overlap this in blue, pretending it's the bending moment diagram. Once it reaches 0 here, right, on the shear force diagram, that's where the max moment's gonna be, right? Because, unless there's point moments or fixed supports screwing with the bending moment diagram, because it'll look something like this, right? Where it corresponds is where the slope is 0 is where it can't go up any further, right? Because you've exhausted all the up area, pretty much, right? Why does it keep erasing? Must be like an update with my app. Anyway, must have changed or something. Okay. So anyway, we're gonna plot this one as well. Okay, so because we don't have a number like +3 or whatever, it's not going to start up here, right? That's only if there's like a cantilever or a fixed support or has a point moment there, yeah? It's going to start at 0, right? Because of how this graphing works. And yeah, and then because I know how the graphical method works, I'm going to plot it first, and then justify the max moment using the functions that we derived, right? So again, it looks like this. Oops. And then here, yeah, let's call that D. Right? All right, we're going to go to our functions here, and we want to find D, right? So, all right, it's basically when the shear force is equal to 0. Yeah, this is just like a graphing thing. So once the shear force is 0, that's where our x is that we're interested in. We're trying to find the x-intercept here pretty much, right? So 0 is this, right? And you want to solve this on your calculator for x, and you can get 1.732 meters, right? Oh, sorry. Yeah, it's x, but we'll just call it d, right? Yeah, that's what we've solved for here, right? So that's 1.732. Okay, and so let's see. yeah, essentially what we want to do is find the maximum moment. So basically we want to find the moment, let's call this point C, or whatever, right? It'd be the moment at point C if we call that point C, but I'm just going to call it max, M max, okay? And that's equal to, oops. That's equal to this pretty much, except we sub in all the x's for D, which is 1.732. Right, and when we plug that in our calculator, we get that M max is 0.866 kilonewton meters. Okay. Yeah. So that's how you would solve that question. And yeah, so basically you have to use the algebraic method rather than the graphical method, because as soon as you get a triangle, triangularly distributed load, it's going to be really hard to find that distance d there without deriving a function, right? And so, yeah, you're not going to be able to find the max moment very easily, right? Because you can't use similar triangles like the slope method, because it's not linear, right? It's just much harder to get. But yeah, we've just been employing a bunch of graphing tricks pretty much throughout this workshop to get it. So I haven't checked the online chat in a while. We're okay. Do we have any questions? No? Are we ready to soldier on? Yeah, all right, let's do this. So, gets even better. So, yeah, I probably won't have time to talk extensively about this question, just because conscious of time. So I'll run you through my thought process, yeah? So I solve for the support reactions first. There's two pin supports here, but because there's no horizontal loading, even though there's a point moment, we can still solve this because there's only going to be two unknowns, which we can split up using some of the moments. And so which method will I decide to use in this question? You can use the graphical method for this part of the beam because it's uniform, okay? And so actually, to save time, instead of doing what I just did above twice for each portion of the beam, from A to B and then B to C, what I've done is I've just done the graphical method down below, and then I just have to take the cut on the right side of it. Yep, so that's the support reactions. What I'm going to do is I'm going to go over to my notes here. Oh, days. All right. So okay, I've just spoiled what I was going to ask, but would you want to go left to right from point B to point C, or right to left? You want to go right to left, because if you go left to right, you're going to see this, right? And then you see this trapezoid, you're like, far out. What have I done to myself, right? So if you go right to left, you're going to see a triangle instead, and then you can solve it much more easier. You don't need to do your integration for like the centroid and yeah, etc. Right? So you want to go right to left pretty much. And plotting is going to take some practice for right to left. But yeah, I've included like full worked solutions and stuff for extra practice on Google Drive, right? But here's how it works. You do the same thing. You do slope, and then the height of that varying height, and just conscious of the point moment here on this part of the continuous beam, not continuous beam, overhanging beam. We've derived our v and x functions, right? And So what I've done is I've done graphical method on the left here. Okay. And the purple part here is what I derived using the algebraic method. Okay. But you have to keep in mind it goes right to left, yeah? So here I've written x in like the x direction that we're considering. So when you plug in 0, x equals 0, it gives you v equals 0, right? And that is corresponding to this point here, right? And one more thing to keep in mind. Do you see how our v and our m, do you see how our v and our m changes directions because of our right to left, right hand side beam notation? Yeah, so just keep that in mind. So v goes upwards instead of down, m goes clockwise instead of counterclockwise. And yeah, and so you can do this if you want. You can get the integral of that shape, the area under that that function by integrating it, right, between x equals 0 and x equals 3, right? And here's how our shear force, our bending moment diagram looks in the end. And you'll see that plugging in x equals 0, m is negative 300, and we're doing right to left, right? So it's that point which is negative 300, and that lines up with our clockwise spin, which causes it to go down by 300, right? Sorry, clockwise spin. Yeah, so sorry, clockwise spin corresponds to going upwards, right? Counterclockwise spin corresponds to going downwards. Yeah. Yeah. So that's all that. I'm not going to do these questions, but I'm going to explain what machines are and why you might find it useful. So again, I don't think this is like formally in the lectures, but I've decided to provide you my like work solutions and questions, like extra practice questions anyway. And yeah, so pretty much here's a frame. They call it a frame, but I don't know. It's essentially machines and frames are very similar. Here we have that pin connection that I was talking about last workshop. And we also have 2 pin supports, which are like normally it would be statically indeterminate, but hinges give you additional information. Okay, so that allows us to be able to solve for this this frame, right? The first thing you do when you're solving a machine or a frame is you can split it up by the hinge, right? So in certain questions, it might look like this, I don't know. Something like that. So you do your free body diagram for this and then for the other one. So it's at the hinge, that's where you split it up, yeah? And you can have, so it's very similar to a pin support, right? Except for pin connections, you have it on both ends that it connects up to the different members, right? Except you have to have the arrows facing the exact opposite direction of what you assumed in order for the maths to work out, okay? So in the free body diagram on the left, I decided to go down and left. I could have gone up and right, and mathematically it would check out. But you just do the exact opposite of what you did for the second free body diagram. And yeah, so I with the free body diagram on the left, I've derived an expression for C, Cx, this one here, right? Which carries over in terms of magnitude to the free body diagram on the right, yeah? And yeah, and then I can get 2 expressions for Cx in terms of Cy. Simultaneous equations, here we go. And then you can solve for the hinge connection reactions. And then, and now you can solve for the support reactions, which is what we were interested in for the question, right? So yeah, that's an example of the machine. Machines might also include pulleys. So if you haven't encountered a pulley much from physics, you can look it up online. Machines also might include springs, which I've included a question of. Yeah, again, I have no idea what's on your midterm. So this is just like, if you have time, you can give it a go. It will improve your theory by doing practice. And your practice gets better by learning the theory, yeah, etc. It's back and forth, right? And so, yeah. Thanks for the time today, especially people in person, staying out so late. Yeah, I'll be around for any questions, but otherwise, thank you for your time, and yeah, it's the workshop. All good. Yeah, bro.
Diagram.
Yep.
So for the triangles, you can't do a point load. You can't use a point load for triangles to find the shear force diagram.
Let me see if I'm understanding your question correctly. So, for example, this triangle, right?
Yeah.
Let me just this triangle.
Yeah.
I mean, you can represent it as a triangle. It'd be like resultant load like that. One third from the fat end, right?
Right.
So the magnitude would be half the area. Oh, sorry, half the base times height, which is the area of this triangle, right, going downwards.
Yeah.
Yeah.
So
Was that your question, sorry? Or?
Can you not do that
Thank
to
you.
find the diagram or?
Oh, right. I see what you mean. So you mean using the graphical method?
Yeah.
Oh, yeah. I guess so. What I mean is, like if you tried to use a graphical method to find the shear force diagram, bending moment diagram for a triangularly distributed load, you'll find that you get up to this step, right? You do this, you know that, and you can kind of tell the shape based on practice like that.
Right. Okay.
But you're gonna have trouble finding that distance here, right? You're gonna have trouble finding 1.732 without having the functions, and you're also going to struggle finding the max moment because of that.
I see.
Yeah.
Okay.
So
Alright.
that's the reason.
Thank you.
Sorry to stress you out, but this is the last time I'm going to be teaching before the midterm, so I wanted to touch on as many things as I could. If there was another lesson, then I'd go slower. But yeah, we had to cover a lot.
Workshop
I think it's next week.
next week.
Yeah, probably on the Monday, I'm guessing. Yeah, what's up, man?
Question about so just now in previous question, there's like an additional moment right here, like a point B. Yeah.
That one, yeah.
So when it's counterclockwise, does it always go down for the bending moment diagram?
Yeah.
So when it's clockwise, then it's going up.
Yeah.
Oh. That's all.
Yeah.
Thank you.
Yeah. All good. Got a question online. Are we able to just integrate the formula we derived for shear force to get bending moment? I've never tried it that way. That you're describing, Mohammed. I mean, it might work, but with integration, just remember how integrations leave a constant behind. So what I suspect is you might run into a problem like finding that integration constancy if you do it that way.
I have a question about like one of the extra practice problems.
Yep. Go ahead, man.
For this one, they're asking for like the moment at point C,
Yes.
and in the solution, like this whole part is just disregarded.
Yeah.
Is that a zero force member, or how?
It's because of what I said at the very end. So I did rush through it because we're out of time. Sorry, one second. I'm gonna undo all my mess before I. So, what did I say at the end?
Thank you.
Yeah, thank you. So basically, for that question, I'll just draw it out for the recording as well. So it's a question that looks like this. This is basically a machine. That's what I'm getting at, right? There's a hinge there, and your supports, right? You do this step, which is you split up the free body diagram by the hinge. So if I want to split this into two separate free body diagrams, I can literally just do that and then analyze only that part of it. So that's why they completely disregard this, because hinge allows you to split up the free body diagram. Yeah,
but wouldn't there still be like the equivalent force?
Yeah.
Like
Yeah.
from.
100%. So that's actually what this is.
Yeah, that's what I thought. So then
Yeah.
like.
So you can call it like, say that's point C, CY, CX, CY, CX, like that or something. So you can either do it as two, like a vertical and horizontal component, or you can, I think you might do it in the solutions like maybe like an arrow that looks like that, and an arrow that looks like that.
Yeah, I know, but like the part that's confusing me is like when they break it up into member like AC, like this long part, like there's no force from that
Oh, yeah.
there, and that's like tripping me out.
That's a good point. It's a very good point.
I'm not gonna lie, I actually took like some statics, like it's the dynamics part that's new to me, but like yeah, this one was just like I didn't quite get it. I was thinking to just ignore it, like it's probably just.
Oh wait. Actually, I think the question is like, what is the
It's asking for
resultant
the.
moment?
It's the resultant moment.
Oh, okay.
So do I just ignore the pins completely, like the supports completely?
I think because, yeah. So when you're doing resultant moment questions or resultant force questions, I don't think you ever need to.
You just ignore the.
Yeah, you ignore
support
reactions. Yeah, pretty much. Yeah. Because.
Yeah. Okay.
Yeah.
All right,
Actually, that's a good point. I never thought about.
Yeah, no,
never
like,
thought about that specific
I didn't think
situation.
about
But
it
yeah.
either. Yeah.
Yeah, but that's true, I think. Yeah. Okay. Thanks for everyone online. I'm gonna sign off now.
Thank you.
Thank you. See ya.